In previous class, we have discussed the basics of amplitude modulation, the power calculation, power analysis, etc., modulation index. Then we tried to understand the generation of AM, and we said that there are two types of AM generators. One is called the low level, another is the high level. In previous day, we have discussed low level diode modulator for the generation of AM, which is called square law modulator. Today we will discuss a kind of high level modulator, and one of such high level modulator is the switching modulator. The circuit diagram for switching modulator is almost identical to that of the previous type of modulator. The only thing is that here, since it is high level modulator, all the voltages, input voltage, are of high level. So basic modulator is this diode. This is the basic modulator. At the input of the diode, we have the carrier and the baseband signal. Here, unlike the square law modulator, we will use this diode in linear region. If you can remember that the IV characteristics of diode is like this. For switching modulator, we have used this knee region, but for this case, for square law modulator, we have used this knee region, but for switching modulator, we have to use this linear region. So let us now see how it works. Since this carrier signal is of high amplitude, so what happens? This carrier signal actually controls the bias of this diode. So depending on the phase of the carrier, the diode will be either in forward bias or in reverse bias condition. So if this one is the carrier, then during this positive half cycle, the diode will remain forward bias, and during this negative half cycle, diode will remain reverse biased. That means diode is actually operating just like a switch, and that switch is actually controlled by this carrier signal. Now when the diode is switched on, then these two voltages will appear here, and when the diode is switched off, then this diode will be just cut off. That means it is open, so the output voltage will be 0. So we can write, if V in is equal to the addition of two voltages, carrier and the baseband signal. Carrier is assumed to be sinusoidal, obviously. AC is the amplitude and FC is the carrier frequency. Now, also we have to maintain this condition for the proper operation of this whole circuit. The magnitude of the baseband signal must be less than the magnitude of the carrier. Both the magnitudes are high, but AC is greater compared to the magnitude of the baseband signal. So under this condition, output voltage can be written as, for ECT greater than 0 and nearly equal to 0 for ECT less than 0. So for positive half cycle of carrier, the output voltage equal to input voltage, and input voltage means both the combination of these two voltages. And during negative half cycle of the carrier, the output voltage is 0. This means that the load voltage V out T varies periodically between the values V in and 0 at a rate equal to the carrier frequency Fc. Thus assume the modulating wave to be weak compared with the carrier wave. We have effectively replaced the nonlinear behavior of the diode by an approximately equivalent piecewise linear time varying operation. Now these equations can be rewritten or expanded in this way. Here this GPT is a periodic pulse train of duty cycle equal to 1/2 and period of the period T0 equal to 1 by Fc. So if we plot this GPT, it will be something like this. Something like this. Obviously GPT is a periodic function, so since it is a periodic function, so we can expand it in terms of Fourier series. So GPT can be written as So if we substitute this GPT in this equation, we can get the output voltage, and we can see that this output voltage consists of the sum of two components. The first component is AC by 2 1 plus 4 by pi AC into EMT cos 2 pi FCT, which is nothing but the desired AM wave with amplitude sensitivity 4 by pi AC. There is another component, rather there are other components. If we put n equal to 2, 3, 4, etc., you will see that the corresponding frequency, if we put n equal to say 2, for n equal to 2, it becomes 3 FC. This one becomes 3, 2 into 2, 4 minus 1, that means 3 FC. So if we put n equal to 3, then it would become 6 minus 1, that is 5 FC. That means the other components that will generate for higher values of n are the undesired components. Undesired components of frequency 3 FC, 5 FC, etc. These undesired components must be removed by use of bandpass filter. Then only the first component will be passed, which is nothing but the AM signal. So this is the basic principle of operation of this switching modulator. Now we are going to discuss the demodulation of AM. Generally, demodulations are of two types. One is synchronous, another is asynchronous. In synchronous demodulation, generally we have an oscillator at the receiver side, and that oscillator should produce a signal that is well synchronized with the incoming carrier. But for asynchronous detector or demodulator, we don't require such oscillator or synchronized oscillator at the receiver. So obviously the cost of asynchronous detector is much smaller or cheaper. It is much cheaper than the synchronous one. When we will discuss synchronous detector or demodulator, we will discuss all these aspects. But for AM, well, AM may be recovered, original message signal may be recovered using synchronous or asynchronous detector, but to make the whole system cheaper, generally for amplitude modulation we use asynchronous detector. Synchronous detectors are very rarely used in demodulation of AM. So first we will try to understand the asynchronous detector of AM. First kind of asynchronous detector that we are going to discuss is the square law detector. the circuit, basic circuit for square law demodulator is this. Here this VA is a bias voltage used to bias the diode near this nonlinear region, knee region of IV characteristics, this region. In this case, in this nonlinear region, current and voltage relationship is nonlinear in nature. So we can write the current is proportional to V square, where V is this AM signal. So current is proportional to AC plus EMT into cos omega ct, where omega c is the 2 pi fc. So this one can be written in this way. This is V square means this square. So this can be written as AC square plus EM square plus twice AC EMT multiplied by cos square omega ct. Now cos square omega ct means half of 1 plus cos of 2 omega c t. Okay, now we have to multiply them. And once we multiply them, so cos 2 omega ct multiplied by this thing will have a frequency of twice omega c, which is very, very high, and that must be eliminated by this filter, this one. So we have to select this C and R in such a way that it is able to reject these high frequency components. Now this one is multiplied with this one. So at the output, what we are getting, V out, what we are getting, this cos 2 omega c term will be rejected by this filter. So terms involving cos 2 omega ct is removed, is not present. So terms involving with 1 will be there. So here we have 3 terms. Forget about this half. First of all, AC square. Now AC is a constant term. So we have AC square by 2. It is a constant term, just a DC. That means it will produce an offset, nothing else. EM square by 2. So EM square means it is the square of the baseband signal. Now the baseband signal, if the baseband signal has got maximum frequency of say omega m, then EM square T will have a frequency of twice omega m, right? So we have to select this combination in such a way that this filter can reject this 2 omega m component, right? So this em square term will also be rejected or removed by this filter. So only existing term is this one. So 2 AC EMT into half means AC into EMT. So V out will be proportional to EMT. That means output voltage is proportional to the message signal. So we can find out, or we can recover the original message signal using this circuit. Now we are going to discuss another detector called linear diode detector or envelope detector. Envelope detector is the most common type of demodulator used in amplitude modulated system. First of all, it is very easy to design and it is very cheap. So the basic circuitry is like this. So basic circuit consists of a simple diode, a capacitor and a resistor. It's a kind of peak detector. So let us try to understand how it works. For this case, the diode should operate in the linear region of its IV characteristics. That means this diode should work just like a rectifier. Now, if the input AM signal is drawn in this way, this is the input signal. Now let us try to understand the operation of this circuit one by one. So first consider there is no filter, only diode is there. So single diode will work as a half wave rectifier. That means the output of the diode should be like this. These portions will not be there. This negative portion will not be there. Only the positive portions will be there. Now let us insert this C and R. What the capacitor will do? During this positive going voltage, the capacitor will get charged. This capacitor will get charged. At this point, the voltage, input voltage will try to reduce, but the capacitor will try to hold this charge. So capacitor will not allow the charge to fall, right? But along with the capacitor, there is a discharging path through this resistance R. So capacitor voltage will not be constant, but it will reduce a little bit depending on the value of R. That means the voltage will follow in this way, this curve. Instead of going to the zero, it will be moved like this. Now at this point, the next cycle has appeared, so the capacitor voltage will also increase. Then again, during this falling edge, the capacitor voltage will reduce in this way. Again, at this point, the capacitor voltage will be like this. Again, the capacitor voltage will be like this. Again, it will be like this, and so on. That means, if you see carefully, that this capacitor voltage drawn in the dotted line is trying to follow the envelope, this envelope, in a slightly distorted fashion. And this envelope is nothing but the input signal, that means the baseband signal, this envelope. So this circuit is able to recover with little bit of distortion the original message signal. Now whole circuit operation is dependent on several factors. If this width is large enough, in that case, this distortion, these are actually the distortions. This distortion will increase. So for higher the carrier frequency, lesser will be this path, so this distortion will be reduced. So more the carrier frequency, better will be the performance. Another thing may happen. If this capacitor and resistors are not chosen properly, what will happen? In that case, suppose capacitor resistance combinations are small, CR small. So what will happen? The capacitor, since R is small, the capacitor will try to discharge through R, and since R is small, so capacitor will lose its voltage much earlier. That means here the capacitor voltage will fall at a faster rate, producing more distortion like this. So instead of getting this signal, we will get a distorted signal, and this distortion is much larger. Now if we make CR large, so what will happen? If CR is made large, then since the capacitor voltage is discharging through this path and this resistance is R, so capacitor voltage will be able to hold its charge for a longer period of time, right? So under this condition, capacitor voltage will be almost horizontal like this. Now what happens here? The next cycle is having lesser voltage, but the capacitor voltage, falling of capacitor voltage is very small. So capacitor voltage will now follow this path. So instead of going in this direction, capacitor voltage during its negative slope of the input signal of the baseband, the capacitor voltage will fall in its own way. So there will be large discrepancies of the original message signal and the output voltage. This phenomena is called the diagonal clipping. So diagonal clipping is a phenomena for which the capacitor voltage, the output voltage of this envelope detector will not be able to follow the original message signal properly, and it happens when this CR, time constant, is very large compared to desired one.